All right, so final thing we're going to want to talk about is called the lever rule. All right, so for this, we're going to have some equations that we've seen earlier. So we'll have, I'll switch colors for this. So we're going to have the moles of the feed equal to the moles of the liquid plus the moles of the vapor. And we're going to have the moles of the feed times the mole fraction of component I in the feed is equal to the moles of the liquid times the mole fraction component, the mole fraction of component I in the liquid plus the moles of the vapor times the mole fraction of component I in the vapor. So these two equations I've shown you before. So we're going to use these to derive this lever rule. So first, we're going to take this and, oh wait, never mind, it's already solved for. So we're going to take this and we're going to plug it in for this F right here. So that means that we're going to have moles of liquid times moles of vapor times the mole fraction of component I in the feed. And then our right side will stay the same. All right, so then factor this out. So we'll have moles of liquid times the mole fraction in the feed plus moles of vapor times mole fraction in feed. And again, the right side's going to stay the same. All right, and then we can get our L's on one side and our V's on the other side. So we'll have, so L times, I'm going to kind of factor them out as I go. So it's moles of the liquid times the mole fraction in the feed minus, those are subtracting it over here, the mole fraction in the liquid is going to be equal to the, so we'll start with this side, so vapor times mole fraction in the vapor minus this mole fraction in the feed. And then we can take V divided by L. So we'll have the ratio of vapor to liquid is going to be equal to mole fraction in the feed minus mole fraction in the liquid over mole fraction in the liquid minus mole fraction in the feed. And so this is our level rule. All right, so you're probably wondering, what exactly does this mean? So to answer that, we're going to take a look at the plots that we made earlier. So I'm going to draw a replica of them right here. So we'll have pressure on the y-axis and then mole fraction from x. And then we're going to have these two curves, going like that, and going like that. And so low pressures, we have a vapor, high pressures, we have a liquid. And in between here, this is where we have a mixture of liquid and vapor. And so that's where we're looking at this. And remember these two curves, those are the dew pressure and the bubble pressure. So basically, if we're at some point, say we have this mole fraction and we want to increase the pressure. So first we'll start with all vapor and we'll keep increasing until we get to this point up here. And this point, that's where we're going to form the first drop, because that's on this dew pressure line. So we'll have a drop of liquid there, and then we'll keep increasing, and we'll get up here. So once we're up here, this point right here, that's Z1, or Zi. And then what these curves mean is that directly to the side over here, and directly to the side. Over here, this is going to be how many moles of, I didn't write that big enough. That's going to be our moles of mole fraction in the vapor phase, while this is going to be the mole fraction in the liquid phase. And then we're going to have this distance right here, and we'll have this distance right here. And these are going to correspond to over here. So this one between zi and yi, that's the distance right there. And this pink distance is that. Alright, so this equation is just the ratio of these two distances as they compare to the ratio of the vapor to the liquid overall. And so as you can see, as we keep increasing the pressure, so we'll have up here, eventually we'll increase it till we're all the way up at liquid. Right here, we're going to have this purple distance there. You'll notice that got longer, whereas this pink distance got shorter. And so the top of our fraction here is getting smaller, while the bottom is getting bigger. And so that means that overall, the ratio of vapor to liquid is decreasing, which makes sense when you think about it. You know, as we keep increasing the pressure, more of this vapor is being turned into liquid. But this equation, the lever rule right here, gives us more quantitative analysis of how that's happening. So that's the lever rule.